So I summarized here the bounds that we were discussing this morning. So this is the standard Hoeffding bound for one function. The true average, so the expectation is less than the empirical plus this term that now we have seen many times, 1 over square root of n. And there is this refined version which includes the variance, or an upper bound on the variance, which is in this case the expectation itself, and which is slightly better when the expectation is small, right? And as I told you this morning, what we want is to improve on this union bound, and one way was to introduce this this prior, if you want, on the set of function. And another way is to use the idea of this variance and to use this parameter here to get a better handle on how big is the class of function. Because so far the only measure of the size of the class of function we have seen is the cardinality itself of the class. Now we'll see that with this trick we can be a little bit more precise. Okay, so let's take a simple example where we have a set of functions, finite, maybe large, but which have the property that they all behave more or less similarly, which means they all make more or less the same predictions, or they make all more or less the same type of errors, right? So this can be quantified. Let's say we even know how different they are. Let's say we know that if we take two functions fi, fj in this set of functions that we have, f, and we look at how many times or how frequently the predictions or the errors made by this function are different, this is small. And we know some alpha that is an upper bound on this. Okay? Then we can exploit this fact in the following way. So we just rewrite things. The difference between, for any function in our class, the difference between true and empirical average is the same thing for a fixed function, any, that we fix beforehand, plus the difference between true and empirical average of somehow the difference between f and f0. Okay? Where f is any function in our set, f0 is something, I don't know, like the center of the class if you want, or any function in this class. Now if you look at those two terms, here we have something that we know how to bound with Hoeffding's inequality because the function is fixed. And here is something we can bound using Bernstein's inequality, and using the fact that now the variance of this random variable is actually controlled by the frequency at which the two functions make different predictions. So we can use then this, like an upper bound on the variance of this quantity here is actually alpha. So essentially the result that you can get is this form. This is the Hoeffding term from the fixed function, and this is the Bernstein term. I've been sloppy about the constant, but that's not important at this point. Where now the log n, which is the size of the class of function, is multiplied by this alpha, which was the upper bound on the difference of the functions. Okay, so what we have gained compared to what we had before is that we have been able to reduce the complexity, or the additional term that we gain from looking at many functions, by the fact that these functions, they are not too different from each other. Right? So we went from log n to alpha times log n. So, and this is the first point where we can introduce what I call the structure or the geometry of the class of function. So, and this is very important. I think maybe that's the most important technical aspect of this lecture, of this set of lectures, is that the complexity of a class of functions depends in a very precise way on how these functions are positioned in the space. So you have to think about a set of functions as some kind of metric space where the functions are at certain distance from each other, and this distance comes from things like this, right? So this you can think of it as a distance between functions. And endowed with this distance, the set of functions becomes a metric space, which has a certain structure. And this structure is the thing that controls how large will the deviation be when you consider, for example, the supremum of the empirical process. Okay? So this was a simple case where we have an a priori knowledge on how similar the functions are, but you can actually go much beyond and exploit more of the structure. So first thing to do is to repeat this construction for the whole set. So what I mean by this is, say you have your set of function from 1 to capital N, and from this set of function you extract a subset f1 to fd with this smaller than n, such that all functions are similar to at least one of these functions, right? So its picture is simple. So you have, again, you can consider a set of functions as some object or some subset of a metric space. And among these functions, so actually here we are considering finitely many, but it doesn't matter. So among all these finitely many functions, you isolate a subset of them, d of them, such that every other function is at least, at most at distance, here I denoted alpha, of one of these functions. Which means that if you were to draw circles, the geometry may not be Euclidean geometry there, but if you were to draw balls, if you want, around these fi, fd, then you would cover the whole space. So all functions would be in one of these balls. Okay? So that's the notion of cover. And once you have done that, you can apply the result that we've seen just before and say, well, if I want to control the deviation for any function in the set, I first find what is the closest function among these cover, f1, fd, and I say the deviation will be those of this function plus these little alpha deviations. And when I do that, I get what are called covering number-based bounds, where I can replace the log cardinality of the set by alpha times the log cardinality plus I have to count how many functions I have in my cover, and this usually is denoted by n of alpha, which is the number of functions I need to cover my space up to accuracy alpha, right? So this construction can be done even if your set of functions, the functions in your set are not similar, but you can extract a subset for which all functions are similar to at least one point in that subset, right? And what will control the rate of convergence of your empirical process will be the behavior of these covering numbers. And a rule of thumb is that more or less covering number at scale alpha for a space, like if you imagine a cube in dimension d, n of alpha is 1 over alpha to the d, right? So if you want to cover a cube of dimension d with balls, you need something like 1 over alpha to the d when alpha is the radius of these balls, and say the cube is the unit cube. Okay. So this is, and what enters in the bound is the logarithm of that. So that's why, and that's something you would obtain. The logarithm of this is something like d times log 1 over alpha. And if you plug it in the bound, you have something like square root of d log 1 over alpha over n, right? So the message here is that if your space of functions were, say, a subset of a unit cube in some space of dimension d, so for example, if you have linear functions with d parameters, then you would have some bound of the order square root of d over n, just by this trick, in a way. Now, you can actually go even further than that and repeat this construction. So here I was using only one scale, right? I covered my class with balls of radius alpha. But if you want to, if you want to capture a little bit more of the structure of your class, you can iterate this construction and compute covers at all possible radius, right? So you start by covering your space with big balls, and then you cover with smaller balls, and you do that. For, let's say, for alpha of the form 2 to the minus k, where k is from 1 to infinity, so it's an integer, or you stop at some level maybe. And what you do is now you look at the centers of all these balls, of the small balls and of the big ones. And when you have a function for which you want to control the deviations, you first look at the closest function in the smallest radius ball, and then you approximate this function again by a larger one. I mean, by a point in the larger cover, and so on. So you construct what is called a chain, and that's why the bound you obtain is called chaining bound. You construct a chain that goes from any function in your space to centers of covers of larger and larger radius. And eventually you will end up in the center of the whole space. Again, this is a picture that does not really correspond to the true reality, because you are not in a Euclidean space. The space of function can be very weird in a way. But at least it gives you the right intuition. And if you do that, if you do this chain, you can actually show that the relevant notion of complexity that enters the bound is of this form, this integral of square root of log n alpha. So it will, again, depend on the rate of convergence, I mean the rate of growth, sorry, of the covering numbers. Yes?
Why do you say that this functional space is non-Euclidean? So the triangle inequality doesn't hold.
Sorry?
Triangle inequality doesn't hold. Or why it's not non-Euclidean?
No, it's a metric space, so triangle inequality holds.
But not every metric space is Euclidean.
But not every metric space is Euclidean, right?
Yes,
Euclidean means you have an inner product, it's finite dimensional, which is not the case. It would be the case if you have linear functions, but if you have arbitrary functions, it's not the case. Yes?
But what if the function space is infinite dimensional? Then the coupling number would also...
This is if you have the whole cube, say. So of course, if you have a function space of dimension d and you increase d and still your functions span the whole space, then you are in trouble, because covering number will explode in a way. But in practice, most function spaces we are working with, say for example function space based on kernels, they have a specific structure. They don't fill up the whole space. They are possibly infinite dimensional, but there are dimensions in which they are very flat. So you have to think of, like, the function space corresponding to a kernel is essentially an ellipsoid in this case a Euclidean space of infinite dimension, which is a Hilbert space. And this ellipsoid, if you look at all the directions, so the principal axis of this ellipsoid, the size of this ellipsoid will become very small as you increase the dimension. So in a way, they are, like, if you look, and that's related to the spectrum of the kernel itself. So you imagine that you have an ellipsoid in infinite dimensions, but the largest dimension maybe is like this. Then the second largest dimension is smaller, and the third one is even smaller, and very fast this size or the radius of this ellipsoid goes to 0. So effectively, this space behaves from the point of view of covering numbers as a finite dimensional space. And that's why it still works even with infinite dimensional spaces. So that's the point. Now, you can actually even go further, but the details become quite messy. Instead of doing these covers in a direct way, you can do it, refine progressively your covers. So you first, and that's called the generic chaining. And it actually gives almost optimal results. You can prove that you get almost optimal results under certain conditions. What you do is you first cover with, say, large radius balls, and then you look at the regions where you need to add more smaller balls to cover the space, because there can be places in your space where functions are scattered. Even though the region is big, there are few functions that are far away from each other, so you don't need to refine too much your cover in that case. And if you do this, then you exploit almost maximally the structure of your space. And well, maybe if we have time, I'll talk about Rademacher averages, but first I'll continue my slides. Okay, so the message is that we have worked with finite classes only so far. I mean, the results were stated for finite classes, but of course, when you start to introduce covering numbers, you can work with spaces of functions that are infinite. But essentially, the message is that the cardinality itself of the space of function is not the right notion for capturing the size, the effective size when you do estimation. A better notion is this notion of geometric structure of the space as a metric space. Okay. Now the other direction of improvement of the bounds, where in my opinion, this is what allows you to get the most accurate bounds in terms of rates of convergence, for example, or at least allow you to capture the right nature of the bounds. Now you can also try to replace, there were these several approximations of the binomial tails. There were Bernstein, Bennett, what I call exponential, and then you can even have exact binomial tails. So doing this would not buy you much. You would gain maybe a little bit in the constants that come in front of these terms, but you would not gain essential insight into how learning within this class of function will behave. Okay, another remark about these bounds. So sometimes the bounds that have this log n term, like for finite set of classes, set of functions, are called occams razor bounds. Because if you interpret them directly, it says, well, the simpler the class, or in the sense of a class having a small number of functions, then the easier it will be to learn in that class. And it's usually taken to justify or to provide the theoretical counterparts to Occam's razor and say, well, if you have a small class, then it's better. So try to find simpler classes of function. You will do a better job. But the point here is to say simplicity. In the beginning of my lectures, I was saying that simplicity is not an objective notion. Which means everybody may have a different view on what is simple and what is complicated. And that was the example of these sequences of integer that a group theorist or a number theorist would extend in different ways. Actually, here we get to some notion of complexity of the classes, or simplicity, it's more or less the same, that comes as an intrinsic property of the class of functions. So there is only one way, once you have a class of function, there is only one way to measure how complex it is from the point of view of making estimation in that class. So if you're trying to identify a function in that class, or if you are trying to build an algorithm that pick a function in this class, then from the point of view of this estimation error or maximum regret, there is only one way to measure how complex this set of function is, and this way involves this metric structure. Yes?
And what do you mean by geometry of the space? I mean, you can just impose some inner product contingent spaces and that will give you arbitrary geometry. I mean,
well, no, the geometry given by the metric which is the difference between the function under the distribution of interest. So this P of F1 different from F2, right? So this is the distance. And of course, okay, this is for binary classification. Sorry?
It's more like topology. It's invariant in geometry.
Well.
So there is
Yes, okay.
So there is this guy Lebanon that does differential geometry. I was wondering if that's what you meant. If these Rademacher averages using differential geometry by just picking some geometry. So
Well, yeah, okay, but here the geometry actually is, yeah, here it's given somehow by the distribution. You don't even know because you don't know the distribution, but you can approximate it by the empirical distribution. But the point is, the geometry of interest is the geometry induced by the sampling mechanism, so by your problem. And any problem induces a specific geometry of the set of functions. And actually, yeah, the point is that it's problem dependent, this geometry.
Doesn't that also imply that your bound is problem dependent? So if you want to say you want to go to 5% accuracy, you don't know, because you don't know alpha without knowing the sampling
Yes, sure. But, okay, the whole goal is to build estimate or upper bounds on these quantities that do not depend on the distribution. So that's one direction. The other direction is to show that there is some kind of relationship between the covering numbers, for example, given by the true distribution and the covering number that you would compute with the empirical distribution. And there are lots of concentration properties that help you do that and that show that you can actually go and directly measure. So you take your function, you look at how they classify the training sample, and you look at, so it gives you a bunch of vectors, binary vectors of size n, and you look at how they are positioned in space. So you look at the geometry of this set of vectors, and geometry of this set of vectors is very much related to the geometry of your set of function under this metric. So then you can actually go and measure the structure on the data. But of course you lose some additional factor, but not very much. Okay, so I guess now the last part of this slide is it's more informal remarks and maybe again repeating these ideas in a slightly different way to get to conclusion on what we can do with all these things. Okay, so there are two things that can be discussed. One, of course, is we have obtained all these bounds in this specific framework where we assume that the data is sample IIDN. What happens if it's not the case? Or actually, it's never the case because you can never check that a distribution is IID. Or you cannot never be sure that your data was sampled from some IID distribution. And sometimes you cannot even show that your data is sampled by from a distribution at all. So what do you do in this case? And the other thing is, we have seen all these bounds, but how does it tell us anything about how to construct algorithm? Okay, so for the IID assumption, as I said, it's very arguable whether it really makes sense, this assumption. But the point is, the result that we have obtained and the fact that what matters, like the quantity we obtain, the geometric structure and all that, this is still true even if we don't have this IID assumption. And why is this the case? If you look at other settings where you don't make this assumption, for example, the transactive setting where what is, so the setting is like this, you get a set of data, you don't know where it comes from, but what you do is you split it into training data and test data. And what is random here is how you split it. And actually that's exactly what people do when they run experiments on UCI databases. They take the database, that's given. There is no way to get more data from this same problem. It's there. And you don't know who created this data set. Maybe it was not sampled IID from anything. It was just given like this. But then what you do is you cut into two parts. You train on the first part and test your algorithm on the second part. And you do that repeatedly. And you say, well, look, I have good result on this UCI database. So in that case, you don't need assumptions on how the data is generated, apart from these random splits. And you can do the same kind of analysis and obtain the same kind of results. Of course, the exact way you measure the distance between functions will be slightly different, because it will not be p, but it will still involve how different the functions are when computed on these training and test samples. Okay, so it will still involve these geometric IDs. Something which is a bit more puzzling, and I really don't have any clue on why this is the case, but it is the case. If you are in the no assumption at all setting, so in the worst case online setting where you assume that the data can be as bad as possible, that it can be even generated, the way the data is generated can change at every step. It can be generated by someone very nasty who wants to make you make as many errors as possible. Well, still, if you look at the regret that you make, so the loss that you make compared to the loss of your class of functions, then you can show, you can have algorithms that obtain bounds on these regrets that have the same kind of shape, which is it's kind of surprising, because this, it seems to be very much related to central limit theorem kind of results here. This square root was the Gaussian part when you take a sum of Bernoulli random variables. Here we have this idea of geometry, but again, everything seems to rely on the probabilities. But if you look at this setting where there is no probability at all, still you would get quantities that are very much the same. And actually you can get, in the binary setting, what is called Radmacher complexity, which is exactly, I did not talk about it yet, but which is exactly what you would get in the random setting, IID setting.
So before in your bounds, these alphas were related to expectations of differences.
Yes?
I mean, what is the expectation over if you don't have probability?
Well, then it's just the difference of the function on this sequence of data that you get. So, of course, you can only estimate it as you go, but it's there. So if all the functions behave the same on this sequence of data, then the regret that you will have will be as small as if you had only compared your regret to one function. So that's the idea. So you still have this same phenomenon. So that's why working in the IID framework is very convenient, and in a way you don't lose anything by making this assumption, because you get the same results if you don't make it. So that's why it's fine to keep working in this setting. Of course, it would be nice to understand better, and that's not the case at the moment, to understand better the relationship between the IID setting and this setting. Okay, now back to the bounds that we have obtained. One thing is that it's often the case that these bounds are very far from the actual error that we make. So if you compute these quantities, I mean, okay, for one function it won't be too bad, and that's what I shown you with these curves. You have this Bernoulli distribution, and you have the bound. It's not very close, but it's not too far. Now, when you introduce these covering numbers or all these geometric quantities, then the bound become very big, very fast. So, and often they go much higher than 1. So often the bound you obtain when you put here the covering numbers for your set of function, if your set of function is not completely simple, then the bound will be much larger than 1 in general. Whereas this, you know, it is less than 1. So it's a bit annoying to have a completely trivial bound, in the sense that it does not tell you anything. Well, it still tells you something, because it tells you that with enough data, the bound goes to 0, so that's already not too bad. But for any reasonable sample size, the bound will be maybe 100. So okay. But okay, so the point is, in the course of deriving these bounds, we have done something non-trivial. And what was non-trivial was not the Hövding or Bernstein part. It's the geometric thing. So how to use these bounds? So if their value is nonsense, what can we do with it? So here I mean, there are other ways to use bounds, but I give you here I call that three levels of using the bounds. One is the quantitative level, which is what I just said, using it to estimate the error. And it's not possible because most often, at least so far, the bounds that exist so far are very large and do not give you any meaningful information about what is really the error that you make. The second level is to use them to do model selection. So you don't care about the value, you care only about the relative value. So you compare two algorithms, you compute the bound for one algorithm and the bound for another algorithm, and if one is smaller than the other, even if they are 100 and 200, you would still prefer the one that is 100, right? And the last one is not to worry at all at the values that you obtain when you compute these bounds, but rather try to understand what you can do with this geometry. So okay, so the first level, as I said, the problem is these are a little bit messy mathematics, right? Binomial tails, they are not very easy to control or to get nice expressions of it. This geometry, again, it's hard to really capture well. And there was also this problem that we have this supremum, but most often the algorithm does not attain the supremum. So all these reasons make the bounds not very sharp. So, and if we want to have better bounds, we would have expressions that cannot be computed or that are completely unreadable. So somehow there is no point in trying to use the value of the bound directly, and the best is to use cross-validation if you really want to estimate the error of your algorithm. Now for the second level, so doing model selection, the only thing you need, in a way, is that the minimum of the bound is located at the right place. So if you have an algorithm that depends on some parameter, say alpha, and you compute the bound that correspond to each value of this parameter, and you get something like this, even if this is, say, 100, whereas so that's the bound, and the true error is something like this, where this is at most 1, right? Even if you have such a picture, what matters is that the minimum here is more or less at the same place as the minimum here, and that would be fine. If you get this kind of behavior for your bound, you're perfectly happy because you can select your parameter alpha from the bound itself, and you don't need extra validation data sets. But okay, I would say in general it doesn't work that nicely. So again, I would recommend not to use it. So then comes the last hope for making any use of these bounds, which is the qualitative use. And again, it's very difficult to actually make use of it, because you can very easily be misled by what you obtain. Okay, so the goal is somehow to use what appears in the bound to get inspiration for making new algorithm or for modifying your algorithm in a way such that it performs better. But in general, it won't give you the optimal value for the alpha or things like this. It will only somehow tell you how where the complexity comes from, or where is it that your class of function may overfit? Why is it that your class of function may overfit? And it will explain this in terms of what is the relevant structure of this class that controls the complexity and the overfitting behavior. So for example, if you take a function class that is parameterized by a certain number of parameters, you would say, well, let's not use too many parameters because maybe it becomes too complex and I might overfit. But then when you compute these geometric quantities for this function class, it may very well happen that after some number of parameters, the complexity does not grow very much if you add parameters. So you would say, well, then it's not directly related. So the number of parameters may not be directly related to the complexity. And actually, you can construct cases where you have infinitely many parameters, but a very small complexity, or a very large complexity with only one parameter. So at least what you can get from this bound is what is the quantity that controls the complexity of my class of function. Okay, but now the risk when you use bound is this, that you may be tempted to justify some algorithm from the bound that comes from the analysis of this algorithm. Okay, so doing this is fine, doing this is dangerous, or even wrong. So why is that wrong? So here is a trick. You give me a class of functions, and I define on this class some functional. So something that takes a function and gives a number. So if I take two values, one is smaller than the other one, the set of functions for which the functional is less than x is obviously included in the set of functions for which the functional is less than y. Okay? Now, if I compute the complexity of this set of this subset of function, complexity in one of these sense that I mentioned before, of course it will be a non-decreasing function of x, right? The larger x, the larger the set, so the larger the complexity. It cannot decrease if you add more functions. So now if I just write down a bound that involves these sets of function, then I will have a bound that tells me the smaller the x, the better, or in other terms, the smaller this functional, the better, right? So I have constructed this way a bound that tells I should minimize this functional in a way. If you interpret it directly, it tells you, well, in your algorithm, try to make this as small as possible, right? And I can put here whatever I want. I can say, well, this is the margin of my function. And then I justify this way maximizing the, this is 1 over the margin, and this way I justify maximizing the margin. Or I can say, well, this is some specific property of my class of function, and then I justify any algorithm that minimizes this property of the functions.
But you can do this a priori also.
Yeah, and that's this prior P that we put this morning, right? But still, it doesn't mean, you can do that a priori, but it doesn't mean that the algorithm should do that to do a good job. It means that if the algorithm minimizes this quantity, and when you compute the quantity on the function that is constructed, it's actually small and you have a small error at the same time, then you're in good shape. But yeah, and okay, that's the same thing in terms of this weighted union bound. So you can do the same trick. You choose a P that gives more weight to function that satisfies certain property, and of course the bound will tell you, or if you look at it directly, it will tell you try and minimize this or maximize the probability, so minimize log 1 over P. But what you should not do from that is this. Should not say, well, because I have a bound that involves this quantity, my algorithm is justified. So that's why it's very tricky, because when you derive the bounds for certain algorithms, you end up with quantities that are either artificial or intrinsic. Artificial would be quantities such that this, or quantities that come from the way you set up the bound, or you set up the analysis. And intrinsic would be the quantities that come from this geometry again. And it's hard to tell whether what you obtain in the bound is really intrinsic or not. So, okay, so to summarize this part about how to use bounds, first thing is forget about the value. I mean, at least now, maybe in 10 years, 20 years, people would have better techniques, but for now, I guess it's hopeless. And rather try to capture the meaningful information that is in the bound and distinguish between what you have put, even without noticing it in the bound, and what comes out of the intrinsic analysis. Okay. So, what time is it? Have time? Okay. Now I'm becoming very philosophical in a way. So now I want to give some remarks or some ideas that are very debatable, but okay, you would contradict me at the end. You will have time for asking questions and giving your point of view. Okay, now back to the design of algorithm. So when you want to design algorithms, I would, and that's very personal opinion, I would recommend to not make assumptions in when you make these algorithms, or at least be sure that these assumptions that you made are really assumptions and they are not something that you believe is true. Unless you really someone tells you that it's true, some expert from the domain that from which the problem comes tell you, okay, this property of the system is true because I checked it or something. But if this is not the case, try not to make assumptions or try not to be too rely too much in your assumptions. And when you prove results, that's where it's even more important not to make too many assumptions. So now, what you can do is two things. So either someone tells you what is the objective, so you want to maximize some misclassification error, minimize some misclassification error, or maximize the money you get from applying a certain algorithm to a certain problem, or anything like this. And then you can, from this, try to derive the optimal algorithm for maximizing or minimizing this quantity. Or you can say, well, let's forget about this and let's try to make an algorithm that estimates everything about the properties of the data. So for example, if you are in classification, you can either try to build a classifier or first try to build something that estimates the densities, how the data is distributed in your space, and then from these estimates, construct a classifier. Right? Most often, you would get the same algorithms. But the point is, if you go with the first approach, it's sometimes a bit more risky because you're trying to do things that you don't have to do or you don't need to do. And you may, for doing that, you may introduce unnecessary assumptions. Okay? But the point is, algorithms are algorithms. They are completely independent on what you may assume about the distribution of the data, and they may work or not work independently on your assumptions just because the problem is nice or not. So, okay, so now the question is, how can we choose the prior? Is there any guidance for choosing the prior? Prior in a very general sense, like what an algorithm should prefer. Well, see, there's not much thing, right? In a way, I've kept repeating during these lectures that all this theory cannot justify the prior. It can only tell you, once you have chosen a prior, whether, the kind of behavior you may expect. So once you have restricted your space of function to functions of a certain form, it will tell you, okay, within this class, you may expect to have such a rate of convergence, but doesn't mean that this class is good for your problems, right? So forget about theory if you want to choose a prior, I would say. But still, you can have some. I mean, I can give you some personal feelings about how to choose a prior. Okay, generally speaking, you want to make operational all the operational in the sense that you can derive an algorithm from it, all the knowledge or belief that you have. But for that, you don't have to follow any specific approach or theory or whatever. It's just be as pragmatic as possible, I would say. Okay, it's a bit messy, this slide. So, okay, so this is a more precise definition of this sentence. So the prior should be what you expect before seeing the data, or assumptions about the function that are likely to solve the problem. Now, okay, in a way, it's just a way to choose between two hypotheses or two functions that look similar on your data. Right? To put it a bit more precisely, a prior is nothing but something that gives you a number or a score for each function. So you have function in set. I mean, you have a set of functions, and what you want is to assign a preference to each function. So you get any functional would be a prior in that sense. So here are few ways to do that. The simplest way is to, okay, again, there are some typos here. Simplest way is to restrict your class of function. So that's the crudest prior. You say, well, I hope that the target function is in this class, and if it's not, too bad. Okay? Or you can have some kind of nested structure of functions classes. So you say, well, I hope that my function is in this class. But if it's not, maybe it will be in the second one. And if it's not, maybe it will be in the larger one, and so on. And to each of these sets, you associate some number that tell you, I mean, ideally it should be something like the complexity of these sets. But it can be anything that allows you to trade off between the error that you make by using function in set and the prior preference that you have on this set. And that's, I mean, here is where theory can give you a little bit of guidance. It can tell you what is the relevant notion of complexity for this set, and hence tell you how you should trade off fit, so errors on your data, and complexity in the class. So is it better to choose a function here which has such an error, or a function here that has a much smaller error, but within a class which is much bigger? And the exact balance between those choices can be given by the notion of complexity that we discussed before. Okay, and then you can imagine more general functionals like a norm of your functions or anything. And usually you do that by, you consider a very large set of functions, as large as you can, because you want to approximate potentially any function, or at least any continuous function, for example, and you want to define a norm on this set of functions. That's the kernel approach. And of course, you have also the kind of Bayesian version or approach of using priors is to define the prior as a probability distribution. But then the requirement is that you need to be able to sum to 1 this probability distribution. So it's not always easy to do it, especially for, like, if you want to put a prior on a very large set of functions, it's sometimes difficult to define a prior that integrates to 1. Okay. Now, how to use these priors? Yes? I think is there some time left? Well, we can have a break actually now, if you want. And I have just a few remarks to conclude, but it's up to you. I guess I have 5 slides to go, so if there is enough time.
15 minutes.
Oh, okay. So then I finish, and then it's over. Yeah. Okay. It's okay. So all these priors, I mean, there was nothing really new in this previous slides, but Now the point is you can use all these restrictions or weights or so on in a general way to trade off between fit and complexity. And that's, I mean, I'm not saying anything interesting here, just saying, well, if you have a restriction prior, a natural thing to do is to minimize the error within the class of function, which is equivalent to what is called maximum likelihood to some extent. If you have these nested priors, you would do something like structural risk minimization or minimum description length. They all look like this. You minimize in a set of function the error plus some term that depends on that measures the complexity of this set of function. Or even further, the regularization approach, it's more or less the same, but here you have an arbitrary functional, and usually you introduce this regularization parameter, which allows you to trade off between fit and complexity. Okay, and of course you can also go via the Bayes approach, where instead of choosing one function, you create a distribution over the function, a posterior distribution over the function, but somehow, or at least if you go, I mean, if you look at the maximum a posteriori function, it will be more or less like if you were doing regularization. So, I mean, the idea is really all of these approaches are essentially the same. You always try to trade between fit and complexity, and what is needed is a guidance for adjusting this trade-off. And the guidance may come from computing or estimating or understanding the complexity of your class in the sense of estimation complexity. Okay, so this is, again, same kind of ideas. But what is important is this last point, I would say. So, of course, priors should be appropriate to the problems that you are looking at. It's good if you can easily adapt them, and that's what makes actually the Bayesian point of view or the probabilistic modeling point of view, where you model everything, all your knowledge as probabilities. It makes it very convenient because you can easily add new information by putting hyperpriors and hierarchical priors or things like this. And they should be easy to manipulate, of course, because in the end you want to make algorithms that minimize this quantity. So they should be somehow tractable, which is now in favor of non-probabilistic method, I would say. So maybe the goal could be like, okay, we have seen that this theory can help you trade complexity and fit, but the goal of another possible goal would be to provide with tools or principles to create priors, in the sense to put your knowledge into operational objects. And kernels, this is a way to do that, where you can incorporate naturally in various kinds of algorithms, you can incorporate naturally knowledge that you would have. Probability distribution is another way, and so it really depends on what is most appropriate for the knowledge that you have. So maybe I'll finish now by listing my favorite messages. So the things that I want to convey to you today. And I guess if you can remember only this is perfectly fine, I would be happy. Okay, so the first point, induction cannot be justified in the sense that you cannot justify a specific prior. You can just say we need the prior. Otherwise, you get all these negative results, no free lunch, and so on. Now, the only thing that you can control, and control in the sense of computing and proving results in a theoretical framework about, is this what I call maximum regret, or estimation error. So approximation error, of course you can prove theorems about it, but for this you need to assume something about where the target function is. Now in terms of the shape of the bounds, like here are the three things that you should remember. For one fixed function, you usually get rate of order 1 over square root of n. If you have n functions and you don't know anything about these n functions, you would get this extra log n factor. If you use the variance and if you are able to bound the variance by the expectation, you would get something like this. So you can improve a little bit this quantity. And if you want to go beyond, then you should incorporate the geometric structure. And finally, when you use the bounds, you should distinguish between first what are the assumptions that you put, and then what comes naturally from the intrinsic properties of the class of function and what you have put manually in the bounds.